Welcome to this online mathematical course on Abstract Algebra. This course is usually taught to second year undergrads in the universities. Now, the aim behind this uh, course or lecture series is to familiarize the students who will be taking abstract algebra in the near future, and it will be much more easier for them to get the hang of the subject if they have some familiarity with the subject beforehand. Else, they are usually lost in the class, and it's very natural to happen, especially when we transit from the high school mathematics to formal university mathematics. The same happened with me as well. So, based on my experiences, I would try to cover up those things which were a problem for me, and it is an attempt to help the budding mathematicians all around the globe. Now, it may seem that abstract algebra might be very closely linked, or I should correct myself, might be very similar to the high school algebra which we used to do. But that's not the case. Here we don't solve linear equations, quadratic equations, etc., or apply binomial theorems directly. However, abstract algebra has been inspired by the high school algebra only. Uh, Towards the end, we would try to see how how the high school algebra is linked and forming backbone for the abstract algebra we have today in the world of mathematics. So, unlike other branches of mathematics like calculus, complex analysis, statistics, etc., abstract algebra does not have a direct application to the real life. However, it has very important applications and very useful applications within mathematics, which make mathematics and other branches of mathematics much more easier. So, to begin with, uh, in abstract algebra, we usually study structures like groups, rings, fields, modules, vector spaces, etc. So, our first object of study would be groups. Now, groups are basically a collection of symmetries of an object. Now, that object can be of any dimension. It may be of 3 dimension or lower, obviously greater than 0, that means 1 dimension, 2 dimension, 3 dimension, or it may rise above the third dimension as well. So if I say that a group is the collection of symmetries of a 1,58,000 dimensional object, it exists and it is true. However, we obviously can't imagine how an object of n dimensional of n dimension looks like. So we would begin with studying the three-dimensional objects and two-dimensional objects or one-dimensional objects, and then satisfy ourselves intuitively, and then would apply the same for the abstract thought that yes, a group is a symmetry of a 50th-dimensional object as well. Now, obviously, we have formal ways to do it, but just to give a hang of the intuitive side, I am saying this and will be trying to illustrate this intuitive way of understanding groups. And very soon we will land up into the abstract definition and the formal definition, which is much more concrete and precise uh, in terms of clarity and mathematical language. As I said, a group is a collection of symmetries of something. These objects can be of any dimension. Now, by symmetry, I mean that symmetry of something is basically a mapping to itself, which preserves all of its structures. Now, technically speaking, this mapping preserving its structures should be a bijection. However, this will be dealt later. But just to give a hang of it, for example, if we consider a simple square, now if we now if I consider an axis coming out of this plane and rotate it along this axis by first pi by 2 rotation or 90-degree rotation, my object, the square, would turn this way, and this would shift the vertices and the points in the square in a way that the shape is intact. So this would happen in such a way. This would become 4 and this would become 3. Now notice that the shape of our square hasn't changed. This shape is still a square even though the points have shifted, the vertices have been shifted. So this kind of mapping helps us to preserve the structure. So, and such a mapping is called a symmetry. Now, if we again rotate it by 90-degree, again the same shift would take place. Become 4. Similarly, so what we have noticed, it has been rotated twice by 90-degree, or it has been rotated by 180-degree. We again rotate it, and then again the shift would take place. And similarly, again rotating it, we come back to where we started from. So after a 360-degree complete rotation, we end up from where we started. So we can say that there are 4 symmetries in this sense. Now if we consider an axis along this diagonal and rotate it along this diagonal, then this would happen in a way like, if we rotate it like this, then this vertex would shift and swap places. So this is another symmetry we have. The shape is preserved, however the points have switched their places. So this is another symmetry we have. Now coming back to what we had, if we consider this diagonal as an axis and rotate it somewhat like this, then these vertices would shift their places and they get swapped. So this is another symmetry which we have. Now one more symmetry is that we consider this as axis and rotate it like this. So this would swap places, this would shift. So this means 2 and 4 come here, and 1 and 3 come here. Now this adds to another symmetry. Now again coming back to from where we started, choosing this as an axis and rotating it somewhat like this, these vertices get swapped. So this gives us 1, this gives us 2, 3 and 4, and this gives us another symmetry. Now observe that there are no more symmetries left, rotational symmetries left for this square. So we know that we have 8 symmetries for a square. Now this was just a recap from high school. We have studied this, that a square has 8 symmetries, and this is how we conclude that a square has 8 symmetries. Now, platonic solids such as icosahedron or dodecahedron, uh, that are basically regular convex polygons, have also symmetry in them. So every polyhedron has an associated symmetry group with it. Now it has a much more general form which we will be dealing with later in this lecture series. So in terms of symmetries, the symmetry group is basically the set of all transformations which leave the polyhedron invariant or unchanged. Oh, by that I meant the same which I explained here. So the symmetry group of this square would have 8 symmetries as its objects, which means these are transformations happening where the coordinates are swapping places with each other and shifting around and moving around from one place to another. However, the shape, the basic structure of the square is maintained without violating it. Hence, the polyhedron remains unchanged or invariant under these transformations. So these are also known as Euclidean isometries. These would be dealt later. Nothing so fancy about it. Now we have some examples. For example, we the same example works for a cube as well, but I would like to take a better example this time. Suppose this is a star we have. I'm sorry. Yeah. So we have 5 points on it. And again we rotate it in a way that it rotates, and these points at rotation by some angle, these points get swapped in a way that they regain this position. For example, 1, 2, 3, 4 and 5, after a rotation by a specific angle theta, the places are swapped as 5, 1, 2, 3 and 4. So as you can see, although this star has gone a transformation, yet the shape is unchanged. Now if you notice that for a complete 360-degree rotation, uh, that means for reaching back from where we started actually, that means from this modified position to reach back 1, 2, 3, 4 and 5, we have to rotate the star 5 times. So this number is known as the order of symmetry. So order is basically the number of times an object has to be rotated to complete a full rotation, so as to gain back the same position we started from. In this case, the star has to be rotated 5 times to complete one rotation and to get back to the same position. Now it's very obvious that if you rotate an object by 360 degrees, it will reach back to its original form, but we have to keep that in mind that the symmetry should be maintained. For example, if I take some irregular polygon, something like this, and rotate it, suppose from this axis, now there is no way I can get a symmetry, rather, or say this shape. By symmetry I mean this shape remains unchanged by any rotation, except for the complete 360-degree rotation. So the number of times I have to rotate this object for one complete rotation such that it is invariant, that is 1. Hence the order of this symmetry or of this object should be 1. So here is the important thing, that while rotating the object, the symmetry should be maintained. The shape of the object should not change. So it is very obvious that rotating any object, whether it's regular or irregular, rotating it by 360 degree, it has to come back to its original position. And to regain its original form, and the points come back to the place where they started from. So the order is the number of times we need to rotate the object so that they complete one rotation, maintaining the symmetries. Now, another example, if we take the integers, suppose we have these points. This can be anywhere in the integer line, and some points suppose this is our integer line. Now I want to make transformations in this line in a way that it remains the same, and by same I mean the symmetry is maintained. So for example, I shift each object with 2 places. That means I shift this to here, this one to here, and this to this, and this goes here, and so on. So I am shifting each point by 2 units. Now, which essentially means that this symmetry is maintained under addition. So if we add by a particular number the whole integer line, then it remains unchanged, and it is it forms a symmetry, and it forms a group. The symmetries of Z of the integer line under addition forms a group. So here I have shifted it with 2 units, I can shift it with 3 units, where in which case I would jump here instead of here. So essentially, now as you can see, this is an infinite line, and there can be uh, infinite number which can be added to any integer. Uh, so generalizing it, in general, the z is symmetrical under addition. So the symmetries formed under addition form a group. Hence, the integer line, the integers equipped with the addition operation, the usual addition we were taught in preschool, gives us a group. Now, again, uh, a very famous example of groups of symmetry is of the Rubik's Cube. It has specific permutations and combinations and have a particular symmetry, and it has to do with groups and symmetries. It will be a fun thing to watch, but I won't get into that. Now, another thing, the star I discussed before this example, so it had 5 points, and we rotated it like this. Now, if you notice, these points can be drawn on a circle. If I draw the figure correctly, then these points are essentially rotating around the circle only, somewhat like this. And with every 1/5 rotation, the shape remains unchanged. So there is a symmetry after every 1/5 rotation, and such groups are known as cyclic groups. The reason, the geometric reason behind calling them cyclic groups is that they can be represented on a circle and having a cycle going on as we rotate the objects. Now, to move on, instead of having a specific object or of any shape, we can have a finite collection of points. Say, for example, we have 6 points. Now, say this point maps to this point, this one maps to this, and this goes here, and this goes here itself, and this maps to itself. Now, for the first point, I have 6 options to pair it with. It can go to this, it can go to this, it can go to this, it can map itself to this, or to itself. So the first point will have 6 options to get mapped to. Now, the second point would have only 5 options left, because the first point has been mapped to a specific point, and since we are looking at bijections, the symmetries are a bijection, it has to map to some other point. It can be itself or some other point apart from the point which the first point has been mapped to. Similarly, the next point would have only 4, 3, 2, 1, and this gives us R6 factorial. So symmetries of finite dimensional objects, the symmetric groups, are denoted by Sn. Now in this case the symmetric group is S6 because we have 6 points and these are the number of symmetries of the group S6, or we can say 720 is the cardinality of this group. So these have been some basic intuitive examples. Now the next example is optional for you for now. If you have some knowledge of linear algebra, then it's fine, otherwise you can skip it and understand it later. So this is an optional example. So the symmetries of a vector space. So the symmetries of a vector space, so we choose our field to be R and say vector space is R3. So say the symmetry is the map, the symmetry for R3 is the map reserving the usual multiplication and addition by the real numbers in R3, in our vector space. Now we all know that from linear algebra that such a map is given by 3 by 3 matrices. Now for these matrices to have a symmetry, it is essential that they have an inverse. I again repeat that for these to be to have symmetries, they have to be invertible. Now again from knowledge from linear algebra, we know this matrix has an inverse if and only if the determinant is not equal to 0. So the reason behind this is because not all symmetries are so the if we consider the case where determinant is also equal to 0, then we are not considering all the symmetries that are present in this vector space R3, because some of them will map to a proper subset of R3. So to prevent this situation that these matrices map to some proper subset of our vector space R3, we need our matrices to be invertible. And for that, we need the condition determinant should not be equal to 0. So once we have an inverse, we consider all the symmetries we have, and hence we get all the symmetries on R3 by this by 3 by 3 matrix, which is invertible. Now there is a very special group called the general linear group, also known as GLN on R. This means the entries are from the real. So this basically is the group of all n cross n invertible matrices, and it is a very special group. Under usual addition, so these were some examples of groups, some intuitive examples, and some examples of symmetries, symmetric groups. So from linear algebra as well, and some from intuitive geometry as well. Now in physics, also the groups have a role to play. For example, the Lorentz group in special relativity, the Lorentz group is group of all Lorentz transformations of the Minkowski space-time. So this is just a small example where groups are used in physics, which is an applied aspect of mathematics. Now, saying that a group is a set of all symmetries, we can formulate some axioms based on the properties the symmetries have. Now, first of all, we can say a group is a set with multiplication. Now, this should not be confused with the multiplication of real numbers. By multiplication, I mean the composition of symmetries. So the composition of symmetries, then notice that the symmetries have an associative property. Also, they have a special and unique transformation which leaves them unchanged. That means there is an identity element. So the identity transformation is basically which leaves the object unchanged, and hence it is a symmetry which does not make any effect on the object. Now, lastly, we can say that we have a inverse symmetry as well, an inverse transformation. Now this can be considered as a trivial symmetry. This is a trivial symmetry because if we rotated some object by theta degrees, we can obviously rotate it back to by theta degrees. So if we rotate it in clockwise direction by a certain angle, we can rotate it by the same angle in anti-clockwise direction, and so on. So this inverse symmetry is trivial symmetry. Now, the goal of group theory, which is the actual aim why we are studying group theory, or rather uh, what we try to do in group theory, is to classify all groups up to isomorphisms. Now by up to I mean that a specific property is taken into consideration, and barring that property, elements of a set or numbers etc. can be considered as equals. Now the ultimate goal of group theory, group theory, is to classify all groups up to isomorphism. Now, by isomorphism, I mean it's basically a bijection which preserves the group operations as well. We will get into the formal definitions uh, very soon, but here is just an overview what exactly the aim of group theory is. It's a simple bijection. That means f of 1, if f is a isomorphism, then f of 1 is 1. That means the identity is mapped to the identity. The group operation is preserved. And inverse elements are mapped to the inverse elements. For example, G to H, G and H are two groups, and F is an isomorphism between them. So these are the rules which are followed, which actually makes it a bijection and hence an isomorphism. So an isomorphism is a mapping which actually preserves the structure. Now, the term up to is quite confusing for many of them, maybe or maybe not. It was for me, and it was a big problem for me for quite a while, so I will try to address it shortly and in a brief manner. So, the concept of up to in mathematics basically conveys that some objects can be considered equivalent under some condition. So, for example, we have a specific condition. So, barring that condition, the objects can be treated as equals. So, for example, the prime factorization of an integer is unique up to ordering. So here our condition is that we have to prime factorize the integers, and we find out that the prime factorization of integers is unique. Now, but if we consider the order of the prime factorization, then it blows up. Now, the factorization does not remain unique anymore. So, that means if I have a factorization of some number, say 2, 3, etc. Now, if I consider this as 3, 2, then obviously these two are not the same. But up to ordering means I have to ignore the order of the prime factors. That means ignoring the order of the prime factors, we get the equivalence between uh, two prime factorizations. So we have to ignore the orders of the prime factors. So essentially it is conveying that the prime factorization PF is unique if ordering is dropped. Now, this is a simple example, and you can uh, take any two integers and work out their prime factorization, and you can see yourself that you take any two integers and prime factorize them, and you won't find that they are similar. So, for example, if some number has if some number has a prime factorization of 2 comma 3 and another number has 3 comma 2, then these two are unique. But if I consider the ordering, then I can reorder them as 3 2, and then it is unique. No, it is no more unique. So if I drop the ordering of the prime factors, then the prime factorization of an integer is unique. So that is what is meant by the phrase up to in mathematics. So in the definition, the sum condition which I am talking about is that we have to prime factorize the integers, and then we get some kind of equivalence. That means uh, the prime factors are unique. Now, in this prime factorization example, no element was equivalent to some other element. That means one prime factorization was not equal to any other prime factorization. In the next example, if say I have a set S and A, B belong to S, and say A and B are equivalent up to X. So this means if X is ignored, X is some condition we have, it can be any condition. So if X is ignored, then A is equivalent to B. In this case, we have equivalence between elements. In the previous example, we didn't have any equivalence, rather we can say the object was equivalent to itself. Now, if we drop X, then A is equivalent to B. So, in this way, S can be arranged in equivalence classes. So this is a basic thing people do in set theory, that an equivalence class partitions the set, and this equivalence relation, that means if x is dropped, then A is equivalent to B, helps us to formulate the equivalence classes. Now the another goal of group theory, the aim of group theory is to classify all ways groups of symmetries, uh, to classify all the ways the groups of group as symmetries of something, uh, which is basically known as the representation theory, where we classify all ways group as symmetry of something. Now, my closing remark would be, how do we know that the three axioms which we earlier uh, deduced from the observation of the symmetries are all properties of the groups? Now, the way axiomatic approach works, we have to believe the axioms and move on and build up. So we have to have some faith, but actually this thing is proven by Cayley's theorem. So the three axioms which came from symmetries is actually all the properties of the group. Now Cayley's theorem actually proves this fact, that symmetries of uh, any object form a group, and these three axioms are all the properties of the group. Now I would like to end this lecture here, and this was just a brief introduction and an overview of what exactly group theory is all about, and it was more of a intuitive approach. So the main thing you need to take with you and allow it to sink in is to understand the concept of symmetry, and how the group of symmetries, the set of all symmetries form a group, and the basic meaning of up to, and the examples I did. If you don't understand the aim of the group theory, like classifying up to isomorphism, or classifying all ways groups can be classified as symmetries of something, then it doesn't matter much. Main things you need to think in your mind is to understand the concept of symmetry, and to understand the basic phrase of up to and the examples. So this will be the end of this lecture. In the next lecture, we will deal with binary operation and basic definition of groups, and some of the properties of groups and binary operations. Thank you for listening me so patiently. If you like the video, then please like, share, and subscribe, and forward it to your friends and family, or any other student who who is a math major and struggling with some intuitive thoughts and abstract thoughts in abstract algebra, it would be a great help to that person and to me. Thank you so much. See you in the next lecture.